Welcome back to physics. This is it. This is the last lesson of the year. At the end of the year, we always ponder relativity. So let's take just a little bit of time today to go into relativity. Relativity is broken down into two different parts, special relativity and general relativity. Special relativity deals with the motion of objects, and general relativity deals with gravitation. To kind of put this in a bigger context, earlier this year, we studied motion, and we studied Newtonian Mechanics. Newtonian Mechanics basically broke down our understanding of how things work in the universe. But Newton lived over 500 years ago, and Newton's theories are not the most current theories. Einstein's theories are. So let's look a little bit at where we've been. So with Newton basically broke down his model into first law, second law, and third law. First law was the law of inertia. Object at rest stays at rest, object in motion stays in motion, unless compelled to change by a net external force. So the most natural state for an object to be in the universe, according to Newton, was for that object to maintain whatever it was currently doing. Second law, if you didn't want it to maintain what it was doing, then what you needed to do was add some extra newtons. Extra net external force causes a change in motion or an acceleration. And then third law, law of interactions, objects interact, they push on each other, they apply equal forces to each other in any interaction. Fourth law then, model gravitation, F equals gm1 m2 over r squared. And in this law, Newton mathematically modeled gravitation. However, he didn't really explain why gravitation occurs. He just gave us a way to be able to calculate it. Einstein pushes further than that. So that's kind of the foundation of where we've been. With any model, with any theory, you have to start with some basic assumptions. So then let's start with the assumptions of Newton so that we can bridge into Einstein. Our basic assumptions of Newton is that, first of all, time progresses at a regular rate. Now, these assumptions are probably things that you and I maybe take for granted. Time. We assume that a second has the same length no matter where you are or what you're doing. In other words, at your house right now, if you clocked off 10 seconds, well, that should be the same amount of time as if we were in the school building clocking off 10 seconds. Or if you went to go visit some relatives in California or wherever, 10 seconds should be the same no matter where you are or what you're doing. That is an assumption that we tend to make that Newton made, but Einstein did not make. Similarly, the mass of an object, the dimensions of an object, we assume those stay relatively constant. If I took an object and put it on a triple beam balance, and I found the mass to be 1.2 kilograms, no matter where I took that object, okay, as long as I still had the same triple beam balance, I should still get the same amount of mass, whether it be at my house, at your house, at school. As long as there's no physical or chemical change, the mass of an object shouldn't change. By the same idea, the dimensions. If we measure the length of, say, one of the lab tables in the classroom, they were 13 feet long. If we moved one of those lab tables to somewhere else and measured the length with a meter stick, with a yardstick, we should get that same 13 feet no matter where the table is. We assume that objects have constant dimensions and objects have constant mass. Now, third assumption. You spent an entire year studying geometry, Euclidean geometry, and Euclidean geometry makes certain assumptions. For example, I have a sheet of paper here, and on this sheet of paper, I have 2 points. Well, shortest distance between 2 points is, hopefully you said straight line. So I'm going to take a second and I'm going to draw a straight line on our sheet of paper. There you go, that's reasonably straight. Now, This is the shortest distance between these 2 points. But what happens if I bend this paper and bring A and B there so they're right next to each other? Now that straight line we just drew is not the shortest distance. Okay? So then if all of a sudden we have a distance that's shorter between 2 points than the straight line, it's going to mess with the geometry that you studied. The basic idea of a geometry is that you start with certain assumptions. Those are called postulates. And postulates can't be proven, but they're generally accepted. From those postulates, you prove theorems, and you extend those theorems, and you go into corollaries. Okay? This bending of the paper kind of contradicts the idea that the shortest distance between 2 points is a straight line. Or we need to think about what a straight line is. How would you define a straight line? Is this a straight line once I bend this paper? By the geometry that you studied, you would probably say it is not. Einstein would disagree with you. He would say, this is the straightest line we can draw on a piece of paper that happens to be bent or warped. He would call this a straight line. Now, if you took this back to your geometry teacher and said, is this a straight line? They would probably say no. Okay. Parallel lines. How did you define parallel lines? Generally, you think of parallel lines as 2 lines that do not intersect. Okay. Well, what if you have a surface like this? What if I draw another line on here? Reasonably parallel. But what happens if I took my paper, and you'll have to imagine, and folded it over like this? Well, those parallel lines are going to intersect each other. I'm just trying to get you to think beyond the geometry that you studied. What if my surface was a sphere? And I said, on this sphere, draw a straight line. Well, then you'd end up maybe drawing a line, and as you went around there, you would end up with something that was curved. And if you went all the way around, you would end up with a circle. So then, are a circle and a straight line the same thing? If you pictured parallel lines going across, well, those parallel lines, they would stay the same distance apart. You could think of them as parallel and they wouldn't intersect. Lines of latitude and lines of longitude on a globe. When we go north and south, all of our parallel lines intersect on the north and the south pole. Are those still parallel? All I'm trying to do is to get you thinking. The base assumptions of Euclidean geometry, there's nothing wrong with them, except they don't apply to the universe. If the base assumptions are flawed, then we cannot come up with an accurate model of the universe. And so then what Einstein did is he created new non-Euclidean geometries whereby straight lines could be bent if the surface they were drawn on was bent. Parallel lines could intersect because the current geometry, Euclidean geometry, was failing in being able to give a way to model the universe. Now, this is kind of where we started with Newtonian mechanics and some of the base assumptions. Now what I want to go into is some of the base concepts and assumptions of special relativity. With relativity, we need to start with the idea of space-time. Space and time are typically things we think of as separate, but Einstein put those together into one thing. So if we were going to define space and time, think about it for a second. What is space and what is time? If we were in class, we would have a long and healthy discussion on exactly what these things are. Space is not an emptiness. It's not a void. Space is actually something. Think about it this way. If I draw a box here, we could let this box be the entire universe. That would be the Earth, all the planets in the solar system, our star, the sun, all the stars in the Milky Way galaxy, all of the millions and millions of galaxies everywhere, and everything between. So the universe really consists of two different things: the stuff and the space. The stuff, again, that's all your planets, stars, and galaxies. Space, that's kind of the region between. It's not an emptiness, it's actually something. Take a minute and take a sheet of paper. And on that paper, I just want you to draw whatever. If you have a normal size sheet of paper, we'll say 8.5 by 11, then what you have drawn is basically stuff on that 8.5 by 11 sheet of paper. Now, what if I told you to draw a line that is 30 inches long? Well, that's going to be hard to fit on a paper that is only 11 inches long. Imagine you were trying to draw, you had your pencil against the sheet of paper, and you were drawing straight, and you kept going, and you kept going. And now what happens when you get to the edge of the sheet of paper? If you're going to draw 30 inches, you would be forced to try to continue to draw, but you wouldn't be able to draw beyond the edge of the sheet of paper because there was no paper there. Paper is an analogy to space. Space, it's something. It's where, in this case, you could draw. In the case of the universe, it's the region where all the stuff exists. So, all the planets, all the stars, all the galaxies, everything exists in this stuff called space. So then, outside of the universe, outside of space, there's nothing there. Nothing is not an emptiness. Nothing is not a void. Nothing is literally nothing. We could talk a lot about that. Have the understanding that space is something. It is kind of that fabric, that region where the things in the universe exist. Time is kind of a measure of when things happen. If I asked you to prove to me that time is passing, how would you do that? Well, one thing, you age. There are other biological processes in nature. Things decay, plants grow, etc., that you could use as evidence that time passes. Time passes whether you're aware of it or not. When you sleep at night, time doesn't stop passing. It continues to pass. So then we've created a system whereby we can measure the when of things happening, but time passes, and our evidence is those different aging and other natural processes. So Einstein took this idea of space and time and said these two things are not actually separate. These two things are actually connected, and that when something happens in nature, we would define that as an event in space-time. Let's talk a little bit about the connection of the two. So let's consider the pictures at the top of the screen. I have a graph down at the bottom, and on the vertical axis we have space, and on the horizontal axis we have time. In our first graph, we have Caitlin and Megan, and they are at rest. If you think of space and time, if you're at rest, you're not really moving through space, but time is still passing. And so if we were to graph that on the graph below, rest would be a horizontal line. We progress horizontally on the graph through time, but there's no change in space. We haven't gone anywhere in space relative to the surrounding gymnasium. In the middle picture there, James is walking. If you're walking, you are moving through space, and time is also passing. And so then if we were going to represent walking, I'm going to draw basically the same line, but I'm going to tilt that line upward, and this is walking. So we've moved through time a lot, but now there's also a little bit of angle, a little bit of vertical displacement there on the space axis. So we've moved a little bit through space and pretty much through time. In our last situation here, remember back from the launching project, many people were running up the hill. So let's consider running. On that graph, if you're running, you're moving more through space and not quite as much through time. So then our line, our event, might look like that. Each of these are events in time-space. Both time and space, there's movement in. Now, to make this more realistic, we're going to associate a percent of the speed of light with these. So at rest, we don't have a velocity. V is equal to 0. When you're walking, let's assume that James is an amazingly fast walker, and he is walking at 50% the speed of light. Running. Let's say that everyone running up the hill, amazing shape and working out during this remote learning, and everyone is running at a speed of 90% the speed of light. In other words, what I'm doing is the normal walking and running would not be fast enough velocities for us to notice the effects of special relativity, but the higher velocities would, so I'm associating a higher velocity with each of these motions, but you still have the analogy to the motions. What I want to point out is, to the best that I could, I drew each of these lines of the same length. In other words, they represent an event in space-time. And so when Megan and Caitlin were at rest, they passed through a certain amount of time. If we go over to James, well, he was moving some through space. And because he was moving some through space, he didn't get as far through time. If we go to all of our people running up the hill, and we extend a line down here on our graph, we don't get nearly as far through time as we did in the other two. So, using numbers, and I'm going to give you analogies because this is a lot to wrap your mind around. Let's say it's the same event, just happening in different ways. So Megan and Caitlin clock off 3 seconds when they're at rest. That's the time interval. They move nowhere through space, but 3 seconds through time. James, when he's walking at 50% the speed of light, maybe he only clocks off 2.5 seconds. So if they could compare their watches at the end of this interval, then Caitlin and Megan would have clocked off 3 seconds, and James would have only clocked off 2.5 seconds, but it would have been the same interval. James moved more through space and less through time. Running, 90% the speed of light. Well, let's say that time interval, they measure off only 1.5 seconds. So then all of the people in the 3 pictures compare their watches at the end, and our group at rest passed through 3 seconds, walking 2.5 seconds, running 1.5 seconds. Their watches were in agreement at the beginning, and they're not in agreement at the end, because the more you move through space, the less you move through time. That's one of your basic conclusions of special relativity. Now, you may ask, well, how can this be valid? I don't notice any difference when I'm walking or running or driving in a car or whatever. I don't notice that time is passing any different. And you're right, because compared to the speed of light, you're not moving that fast. For you to notice these changes, you would have to be moving 50% of the speed of light or higher. We don't move. Speed of light in miles per hour is 186,000 miles per second. We don't move anywhere near that in everyday life, and so we don't notice these effects. But experimentally, atomic clocks, which measure time out to like 9 decimal places, one atomic clock on the ground at rest, one atomic clock placed on an airplane, flown around for a while at higher speeds. The clock's in sync at the beginning. When the plane lands with the second atomic clock, they're no longer in sync. The one that has been flown on the plane has passed more through space and less through time, so has clocked off less time. This is called time dilation. Particle accelerators. Particle accelerators, when they are programmed to accelerate particles up near the speed of light, must be programmed using Einstein's equations for time dilation, because particles are not getting to their destination when we think they should, because they are passing differently through space and time than we are. So there's a lot of experimental evidence that time dilation is a more accurate way of thinking of our universe than some of the base assumptions and understandings of Newton. Let me make this a little bit more concrete in a couple of different ways. Let this top black line represent an event in space-time. And what I have is that same event then divided up. If you're moving slow, then some of this movement is through space, but most of this movement is through time. If you're moving faster, then more of this movement is through space, and less of this movement is through time. So this would be the, say, 2.5 seconds versus 1.5 seconds that we pondered on the graph a minute ago. The bottom line there. Well, before we get to that, I'm going to hop back to here for a second and do a little what if. Well, we went from rest to walking to running, and each line progressively got steeper and steeper. What if we had a line that went like this? That vertical line, you would be basically moving at the speed of light. If you're moving at the speed of light, you have maximized your movement through space and minimized your movement through time. In other words, it's kind of the complete opposite of rest. At rest, you have minimized your movement through space and maximized your movement through time. So back on that vertical line, what would that look like if you were moving at the speed of light? You would pass through space at a maximum rate, but there's no horizontal displacement on the graph. There's no movement through time. So then what would that mean? Say you decide, I got to take a break from pondering relativity and go outside, and I'm going to walk down to the store or wherever. How long would it take you to get there if you were moving at the speed of light? You'd be there in no passage of time. If you were moving at the speed of light, it would take you no time to get anywhere because time is not passing. So you are here at your house and you are at the store at the same time, but then time wouldn't really mean anything because time's not passing. So then maybe the bigger question would not be how long does it take to get somewhere, but the bigger question would be, where are you? If it doesn't take you any time to get anywhere, then you're at your home and the store at the same time. You're at school, even though campus is closed, at the same time. You are in California. You are on the other side of the world. You are somewhere else in the universe, all at no passage of time because time is not passing. So then you're actually seeing all of space, being everywhere in space at no passage of time. Yeah, there's a lot to think about there. And just a side note, we've never gotten anybody the speed of light. We've never gotten anybody near the speed of light. And what it comes down to, is our base equation of E equals mc squared. As you go faster and faster, then your total energy increases. Not only do you have the rest energy associated with your mass, but you have additional kinetic energy. And if you have a larger value on the left side of the equation, then, and it's equal to the right side, something must be larger on the right side. The speed of light can't change, and so what changes is the mass of the object. As we accelerate objects up to very high speeds, approaching the speed of light, this is mainly atoms and atomic particles, we observe their mass increases. So we have never reached the speed of light with a person because they get too massive. A spaceship gets too massive. So particles we can handle. People, ships, not so much. So this bottom line would basically be moving at the speed of light. Time would not be passing, and you would be moving everywhere through space. So then kind of bring this into kind of balance. That first line would have been at rest, where you were moving through time, but not through space. Let me give you another example that is a little bit more concrete. Imagine we have two twins. Well, we don't have to imagine it. We have some twins. We have Mackenzie and we have Haley. Identical twins, and they decide to explore this idea of time dilation. So we're going to put Mackenzie on a spaceship, and we're going to send her on a trip out through space, traveling very fast. What does that mean? 95% the speed of light. While Haley is going to stay back on Earth, and basically she's going to remain at rest. So then here we have our situation. There's Haley on Earth. There's Mackenzie headed out into space. Let's say that she travels out through space at a very high speed for a time that she measures to be 1 year. So then here she goes, blasting off. She travels out for 1 year. And then she stops and she turns around, which means it's going to take 1 year for her to return. Mackenzie has clocked off 2 years. She is 17 years old right now. Higher level math here, +2. She returns. She's 19 years old. Left in the year 2020. So then, by her clock, she returns in the year 2022. Haley back on Earth, basically at rest, which means that she is moving more through time because she is moving less through space. So then, identical twins, same age, both 17 years old. So when Mackenzie leaves, she's 17 years old. Haley watches, waves goodbye. Mackenzie leaves. Haley clocks off, knows her sister's supposed to return in 2 years. Her sister doesn't return in 2 years, doesn't return in 3 years, doesn't return in 4 years. She waits for maybe 20 years. Now it is the year 2040. And thank goodness the coronavirus is gone. 20 years later, well, now Haley, that would be simple math, 17 years plus 20, she's 37 years old. Mackenzie has traveled more through space and less through time, and has only aged 2 years. Haley has moved less through space and more through time, and has aged 20 years. So now, if we look at them, there's Mackenzie and there's Haley. Identical twins, but Mackenzie has moved less through time because she moved more through space. Halley has moved more through time because she moved less through space. So then their ages, 19 years old here, 37 years old there. Mackenzie says that the year is 2019. Halley says that the year is 2040. Who's right? Well, to define who's right, we need to think of who would we agree with, and we would be on Earth with Halley. And if we're on Earth, we're going to say the year is 2040, which means that Mackenzie has traveled into the future. Mackenzie has traveled into the future by slowing her own passage of time down. So she traveled more through space and less through time. And when she stopped traveling, she stopped in what was our future, because we had traveled more through time and less through space with Halley. Difference in movements through space and time. All this is experimentally verified, not with people, with particles. They live the rest of their lives being different ages. Mackenzie picks up at 19, and now she has rejoined our movement through time. She ages normally, but they live the rest of their life being 18 years difference in age. Let's say biologically they are destined to die when they are 80 years old. When Halley hits 80 years old, she dies. 18 years later, when Mackenzie hits 80 years old, she dies. Okay, so they continue their aging processes from where they are, but now they're passing through time at the same rate once that Mackenzie has returned. So Mackenzie starts to have second thoughts, and she goes back to here and says, well, can I go back? I kind of really miss those 18 years with my sister and all my friends, and I want to go back. By relativity, time travel into the future is possible by slowing your own passage through time down. However, there's no way to go back. The best you can do is slow your passage through time down and travel into the future. But you cannot go back. Mackenzie has no way of being able to recapture those 18 years that she lost with her sister and her friends. She will just have to live being 18 years older than them for the rest of her life. Now, this gives you a little bit of a flavor of special relativity. General relativity gets into gravity and explaining gravity as the idea of warp space. But that's a whole nother lesson, and I don't have time for that one today. It has been a pleasure pondering. Wish we could have pondered face-to-face some of these topics of the last couple months. But hopefully you have had a wonderful time pondering and are looking forward to a break this summer. I look forward to hopefully seeing you next school year. Have a wonderful day, and always ponder.